The first one is perhaps the most common application for the boost converter, which is in switched mode power supplies for power factor correction. And what do I mean by that? I want to create a system where the input current of a switched mode power supply is sinusoidal and in phase with the grid voltage. That means unity power factor. Well, how does this converter operate in this scenario? It's basically this generic diagram here, right? So instead of having a rectifier with a very large capacitive filter, which causes the input current to be very pulsed, I'll use a rectifier with a tiny insignificant capacitor that doesn't make much of a difference. This makes the output voltage of this rectifier have that full wave rectification shape, right? Yeah, and I add a boost converter that will control the current in this inductor so that it has the same shape as the voltage at the rectifier output. If I can do this, when I look at the grid, my current will have a switched sinusoidal shape. Alright, and obviously it's a boost converter, right? So that means the output voltage of this converter has to be higher than the input voltage. Normally, these converters operate with an output voltage in the range of, say, 300 something to 400 volts, alright? Then I have the switched mode power supply itself, right? A flyback converter, a half bridge, or something like that, which will then power the loads of this supply, okay? I have brought this piece of equipment here for us to examine today. I am able to operate this device in two distinct ways, either in critical conduction mode or alternatively in continuous conduction mode. I have already gone ahead and run a detailed computer simulation for both of these specific scenarios. The very first graph that you see here clearly displays the grid voltage alongside the current. You can see that I have a sinusoidal voltage, obviously, and a sinusoidal current as well, right? But it's completely switched. The second graph shows a bit of the control. So I have my voltage at the rectifier output there, which you can see has that full wave rectified shape, right? In orange, I'm not even sure if you can see it clearly, but in orange, I have my current reference, which my control uses. And you can see that the current in my inductor, which is this blue current, switches from 0 to the reference current. So I'm literally starting from 0, reaching the reference current. I turn off my switch, it goes back to 0. Then I turn it on again, and I keep performing this operation in critical conduction mode to operate this device. Then why do I use critical conduction mode? Because smaller inductors are much cheaper. However, I then need the grid side harmonic filter to handle the switching. So I save on one side, but pay for it on the other. The output voltage is about 400 volts. Well, I can also operate this in another way, using a slightly more sophisticated control, where I will have continuous conduction mode operation, which is basically this scenario here. You can see that continuous conduction mode means the current ripple in my inductor is a bit lower, right? This makes the input current waveform a bit cleaner, a bit more sinusoidal, right? Yeah, and that's basically what I'm going to do. So I'm going to build this power factor corrector by controlling the inductor current the way I want. I'm going to impose the shape I want using feedback control, all right?